Hi everyone. Um, we're going to look into this topic on Perceptron neural network architecture. Perceptron is a network. It is to map simple data set. To map complex data sets, we need backpropagation. This is the topic we'll be covering later on. But Perceptron is most basic neural network architecture developed early 80s. It can map. That means it can. So if you have a simple measurements, then those measurements can be stored into this network. What we're going to look into this in this topic, we're going to first look into the first is for any given neural network architecture. It will have three basic elements. It would have what is called the specific type of topology, specific type of neurodynamics, and also it has got its own type of training algorithm. We're going to look into one by one each one of them. Neural network architecture first, its topology, training algorithm, and also neurodynamics. Then we'll look into the specific type of neural network, perceptron network, how a typical network would look like. First, actually, we'll describe through the topology a generalized network, how it consists of and what it consists of. Then we'll look into a specific implementation of the perceptron neural network architecture as to how to map certain data set into the network. That's called the training of the perceptron. And then once you train the network, network can be used for practical use. That is, for any given set of inputs, it will recall the nearest match. That's called recall mode. So then we look for a best way to understand any neural network is to go through some numeric example. Start with some data set and what is that data set is, and how it is training is done, and how the recalling process or testing process is done. So if you first look into this topology, again more details of this are indicated on this page. There was summation functions and training algorithms. And if you look into the documentation on Perceptron, it would have all the basic introduction on neural network first. That is the sections 3.1 to 3.2. Section 3.3 has got a specific computer program that does essentially Perceptron neural network simulator. That obviously runs both in training mode and as well as in recall mode. And it also shows examples how to run it and how to capture it, and also the details of the simulation trace, what the individual values are and how they are obtained. Details of these programs are listed in this topic. In our case, we are going to look into a specific type of program, a specific data set, and we'll train it and we recall it. Now, okay, if you look at the neural network architecture of the Perceptron, this one has let me see if I can. As you could see, Perceptron is a two-layer network. It has got an input layer and it has got an output layer. All the input layer, and then we have for each of this layer there is a term called the bias term. This corresponding to we have studied what the threshold logic. The bias term usually refers to setting up the threshold for a specific given single threshold unit, or in this particular case for the entire network. Bias term is quite often referred to as a zeroth term. There is no input for this element, and the output is always going to be 1. In this Perceptron neural network, we got the input layer and output layer. Input layer is the primary inputs are specified as X. These primary inputs are connected to the input layer through a set of randomly connected weight. It's called fixed random weights. Reason we call it fixed, this the elements of B element is connected, fully connected, that is say every element, whereas the primary inputs are connected to the input layer through a at random with 50% connectivity. So if you have a 6 element, on an average about 3 elements are connected to each of these elements in the input layer, and the corresponding each of these element will have it will generate each of its own internal activation. When you apply the corresponding transfer function, that is in this particular case a linear transfer function, it will generate y output. The corresponding the weight matrix from the primary inputs to the input layer is called the WN, that is input layer weight matrix. Similarly, when you go from input layer to the output layer, these connections are fully connected, and these weights are going to be adaptive random weights, vary between -1 and +1, and the corresponding the bias term is fully connected. Again, this is fully connected, that's fully connected, and all the weights are adaptive random weights. That means that during the training, these weights are modified, these weights are modified, whereas when you say fixed during the training, these values are not modified. What it means is when you apply a primary input X, that value of the output that are computed, In and Yn, remains same thing, because the primary input remains same and the weights remain same, and therefore corresponding output vector that is generated out of the input layer is going to be fixed. So if you take this the input layer here, again the neurodynamics is specified through the what is called the summation function, transfer function, and LR is the learning rule, that is the training algorithm. In this case, it uses the standard weighted summation function, both the input layer and the output layer. Input layer uses what's called the transfer function linear. Linear means in this case the for a linear transfer function for I equal to y, so there is no modification that is done, whereas the output layer transfer function is a perceptron. What it means is it is the unipolar linear. What it means for I greater than 0, y equal to I. If I is less than 0, y is going to be 0. That means output y from here, it is going to be unipolar continuous. Whereas here it is going to be whatever the form of the input that you have, output is going to be done. It could be unipolar, it could be bipolar. Whereas the output from here is going to be unipolar continuous. Again, as indicated here, Perceptron two-layer network with the fixed input weight matrix W in and adaptive weight matrix W out, which is here. Initial networks, initial network random weights are between +1 and -1. It is a feed-forward network with the input layer is randomly connected with 50% connectivity and fixed weights. However, the bias term is fully connected in both cases, whereas the primary inputs are connected with 50% connectivity. Output layer is fully connected, including the bias term B and the weights are adaptive weights. That is, this is fully connected and that is fully connected. The weight, the training algorithm, that is called the delta rule. In this case, weight change is given by TC, trailing coefficient, sometimes called alpha, times the input activation I minus D minus Y, D minus Y. D is the desired value at the output, and Y is the correspondingly computed value from the network. Obviously, the amount of weight change that you want to make will be proportional to the amount of error that you have. What is your desired value and what is the your computed value? Higher the difference between desired and computed value, the higher the weight change that you would make. Of course, it also depends on the input activation. Next, let's look in. This is a typical the Perceptron network. This one is a it's a 6-4 Perceptron network. Sometimes it's called the number of elements in the primary inputs are going to be equal to, sorry, again here this network is a 6-4 network. In this particular network, the first this is the primary inputs which are indicated by these dots, and the neurons are specified always by circles. So this is the primary input vector, and this is the input layer, number of elements in the input layer. Always for this particular network, what I have seen through this software is the number of elements in, and whatever the number of primary input that you have, the input layer would have the same number of same as the number of primary inputs. So if you have 6 primary inputs, input layer would automatically would have the 6 inputs, input elements. That's why it's called, simply sometimes called only 6-4, means you would have a 6 in the primary and 6 in the input layer, and you had 4 elements in the output layer. As you could see here, by definition, remember that on an average about 50% of the input element, 50% of the input elements are connected to input layer elements with the 50% connectivity. So if you have 6, on an average you would have 3, any 3 are connected to one of these 3 elements. So there are no set pattern here, they are just random connections. Only each one of them will go to, on an average, to 3 elements. You could see the bias element is fully connected. So what it means is it goes to the element number 1, 2, 3, 4, 5 and 6, whereas these inputs 1, 2, 3, 4, 5, they are connected to the input layer at with only 50% connectivity. So whereas if you look for the and 0 being the bias element, again there is no input for this one, the output always going to be 1. Here when you go to the weight matrix from here to here is called the WN weight matrix. These are going to be source and these are going to be destination nodes. Similarly, when you go to the output weight matrix, these are going to be your source elements, and these are going to be your destination outer elements. So this network at the output, every element here is fully connected. That means if there are 6 inputs plus the 0th element, bias element, there are 7 elements here. Those each element here would have 7 inputs. 6 from the elements plus 1 from the bias element, so only 7 elements. So you got 7, 7, 7, 7. So here on an average we don't know how many inputs are going to be, because these connections are random connections. Only for sure you will have 1 connection from the bias element, but how many of these are connected to each of these elements we don't know, because they are random connections. If you look at the weight matrix WN that we have here, you could see that that is indicated from see here 0, 1, 2, 3, 4, 5, 6. These are going to be 0, 1, 2, 3, 4, 5, 6. Those are called the source. That is indicated of W ij. This is I, and that's going to be j. And the again now this weight matrix is specified as the source to the destination. In this case we have sources, those are indicated as W of ij. The weight from here to here is called a W of 0, 6. That means the source is 0 and the destination is 6. In this case here this represents I, and this represents j, W of ij. So this weight is from W of 0, 1, this weight is W of 6, 6, and so forth. So in this case the total weight matrix is going to be source is going to be 0 to 6, 0, 1, 2, 3, 4, 6, and then destination is going to be 1 to 6. That is going to be 1, 2, 3, 4, 5, 6. Again, remember the input that we have, they are not going to go to the bias element. Bias element is subtly added element. There are no inputs for the bias element. The output is always going to be 1, and output always going to be 1 here. Output. In this case the another thing that you have is some of these things networks are indicated as NC. That indicates no connection. So be remember, because these are all randomized connections, some of them are connected, some of them are not. For example, if you look for the 0th element, which is the bias, it is connected to 1, 2, 3, 4, 5, 6. That is connected to 1, 2, 3, 4, 5, and 6, and therefore you have all the weights. But whereas if you go to the element number 1, element 1 is connected only from 0 to 0, and is connected to 1 and also connected to 4, but it's not connected to 2, 3, 5, and 6. So if you look for the element number 1, that is the element number 1, it is connected to 0, 1, and 4. Sorry, 0, 1, and 4. And it is not connected to 2, it's not connected to 3, it's not connected to 5, it's not connected to 6. So it's not connected to any of them. Those connections are indicated as no NC, no connections. It also indicated as when you are computing the values, that's equivalent to W weight of W equal to 0, which is fixed 0, and when it is written into the network, sometimes it's stored as 99 for simplicity. If you look for the similarly, if you look for this, this is called the input weight matrix. In this case, input weight matrix is a 7 by 6 weight matrix. Where when you look for the output weight matrix, similar to this, here the inputs are going to be again from 0 to 6, that is 0, 1, 2, 3, 6, that is the input layer elements, and then output is going to be 4, that is going to be 1, 2, 3, 4. So again, this is 0, 1, 2, 3, 4, 5. These are source, that's a W of ij. These are j's, and these are going to be i's. So this one, it is fully connected, and are all adaptive weights, and therefore you have all the weights for every element to every element here. So if this one is a W of 6, 4, that is the element from 6 to 4, and that weight happens to be 0.2, that is 0.20. And if you take say to 6, that is from 0 to 4, that is 0 to 4. You see that's 0.26, and so forth. Basically, when you do this network calculations or network training, the way the activations are computed would be when you apply your primary input here, you will go and compute the internal activations and the corresponding activations here. Use these input y input activations from say 0 to 6 to compute the value of input activation at the output layer, and also corresponding output activations y out here, I out and y out here. In and whereas and yn here is going to be I out and Y out. The process of going through applying your input X and then computing the value of in, yn, and using this yn to compute your in and I out and corresponding Y out is called one forward pass. That is, the networks are going through applying your primary input X. In this particular case, specific input of apply, then you compute in, use this in to compute your yn. Once you have this, and you apply this to use these yns to compute the values of I out, then use the I out to compute the value of Y out. And of course, at this point, whenever you train the network, you have, this is going to be your measurement input. Each measurement you have an input, and also you have the corresponding computed output, that is the measured output value, and that's going to be your desired value. So for a given sample, you have a xi, that's going to be your di, desired value, and then when you do this, you get activation, that's the computed values. So based on the computed values and the desired value, then actually we know how much is the error. Based on that, we can actually make corresponding corrections or training, and that's what we will be doing in the next section. So that's the moral, the perceptron network consisting of essentially 2 layers. With this, all the weights here, they're fixed. Only these weights are going to be modified during the training. Okay, now we'll go through a specific example of how to train this network, how to map the data. Now, in this case, we have a specific data. This page indicates how the network is. Take a specific example, and then train this network. The data set that we are going to map would be, in this case, for the sake of simplicity, I have used the binary values, but in real networks you can have continuous inputs here, and also you can have continuous output here as well. So in this case, if if the input is like a 1 1, if its input is 1 1 0 1 1, my corresponding output should be 1 0 0 1. Again, the 0th element is a bias element that's fixed equal to 1. So the inputs are, if I have 1 2 3 4 5, if I apply 1 1 0 1 1, at the output I had to get 1 0 0 0, and that's my desired thing. When you train it, that's how it has to train. Again, it reads the input data from a specific input data file. You can actually look into the simulation input file. In the simulation program, this Perceptron program 3.0 or whatever the newer version, this is the input data file. The input data file for this one is going to be the input layer Perceptron network in file. You need to specify the number of elements in the primary inputs, and also the input layer. In this particular case is 5. Then you need to specify how many elements that you have in the output layer. That is in this case is m, number of elements in the output layer. Then you need to specify the alpha, which is called the training coefficient. Then you specify what is called the TSS/TH, desirable threshold error. That means when the network is trained, if the desired value is a 1, it would train better than 0.8. If the desired value is 0, it will train the output such that it will be less than 0.20. So for a 0, it will be less than 0.20, and if d is equal to 1, it will be greater than 0.8. That's called 20% error. So it will be less than 0.2 or greater than 0.8. In this case, you can actually train any number of input patterns. In this case, we are going to train whenever you want to understand how the neural network works. You should apply one pattern. In that case, it will display all the internal details of how the network training is performed. On the other hand, if you want to use it in application mode, when the patterns and number of patterns are more than 2, in this case you will skip all the printing of all the details of training. So in that case, you can use it for application purposes again. But if you want to understand it, you just run with one pattern. In that case, it will display all the input detail. Again, the program, what it does is first actually reads this input data and redisplays it, so we know actually what is being read. So in this case, corresponding to this one here, actually 5 is the number of elements in the primary inputs on the input layer, that's going to be 5. The number of elements in the output layer, that's going to be 4. And alpha is the training coefficient is 0.5. TSS, the desirable threshold is 0.8. Number of patterns to train is 1, and the pattern association to trap is corresponding with the patterns. Of course, in this case, p equal to only 1, and the corresponding element 5, that is 0, 0. Again, this is not entered. This is just added. This is 1, 2, 3, 4, 5. That is corresponding to say 1, 1, 0, 1, 1, and then the desired value is going to be 1, 0, 0, 0, 1. That's the output. That's the output value. So this display simply this data is displayed here. So the now what we are going to look in, let's see how this network is. So once it is done, initially what we will do is you start with some randomized values between plus minus 1. It will never be plus 1. It will never be minus 1. It will be definitely less than greater than minus 1 and less than plus 1. So obviously those numbers you will never see a 1, plus 1 or minus 1 here. So the primary inputs are, we don't know what the input weight should be after training. So you start with the random values for the input weight matrix as well as output weight matrix, and those happens to be the values at the beginning. And correspondingly, once that is done, you have the input weight matrix, you got the output weight matrix, then you have X input. Once that is done, what you want to do? You want to do what's called the forward pass. Forward pass means you apply your primary input to the input weight matrix, then you compute your IL and YL here, then use these Y in values to compute the value of Y here. These are the internal activations of the input layer or output layer. Internal activations are indicated as sums, which is nothing but weighted sums, and the corresponding output values are indicated by ACT, which is the activations. This is YN, this is your IN. Similarly, this is I out, this is Y out vector, this is I out input vector. These are the corresponding elements of the elements here. Obviously here we got the first element, that is IL of 0. Obviously that IL of 0 is nothing, output is fixed, which is the bias element output of the input layer, that's fixed value. And you got is 1, 2, 3, 4, 5. So you compute your I1, I2, I3, I4 and I5, and here is the corresponding values are going to be that's I, Y in 1, Y in 2, Y in 3, Y in 4, Y in 5. Okay, to compute these values here, to compute the value of the weight matrix IN, here this network is let's see actually how you got this the IN for the input layer element is 1.12, and let us see how this is computed. Again, to compute the value of the fifth element IN, we need to apply the primary input vector X to this element, and so the when you apply this input, the corresponding weight matrix is going to be here. So in this case, you use this each one of them. If you multiply this vector with this vector, that is the weight matrix of the first row, you'll get IL1. If you take this and multiply it the second row, you'll get I2. If you multiply this input vector multiplied with this fifth vector, you'll get I5. To get I5, you multiply this vector with that one. To get I4, you multiply this vector with the same input vector, and so forth. So in this case, if we want to compute the I5, you would see that the input vector is the same thing, which is the 0 that is fixed at 1, and the input element is 1101, that's 1101. And to get the IL value, you take this weight matrix 380642 NC38, and then you multiply. This is the input vector X, and this is the corresponding weight matrix for the IL5, that is the weight matrix IL5 here, that weight matrix. If you multiply the corresponding element, you will get Xi times Wi. That is here is going to be X0 times W0, X1 times W1, X2 times W2, X3 times W3, X4 times W5, and X5 times W6. So if you multiply the corresponding element, 1 times 0.38 is 0.38, 1 times 06 is 06, 1 times 40 is 42, again 0 times NC. NC is a 0 value, so irrespective of what the value you have, that's going to be 0. It doesn't matter even whatever value that you have, this is going to be 0. 0 into anything, whether you have 1 or 0, still is going to be 0. This is also going to be 0 irrespective of the C. N equal to 0. This 1 times 0 is still is going to be 0. So if you add up all of them together, you would see 0.3806 plus 0.42 plus 3.38 and so forth. You will get a 0.12. That's going to be I'm sorry, this is there is a type. If you add this 0.38, 0.064238, this thing, what you get is 1.12, not 0.12. That's a typo there. So when you add up these values, you'll get that value. Similarly, again, for the input layer, the transfer function is a linear. What it means, I equal to y. That means if it is 0.84, that's going to point out I equal to y. That's I equal to y, I equal to y, I equal to y. So there is no transformation done on the activation function. So similarly, if you have another example here, if we take the element number 2, IL2, to get this value, you have to take this input vector X multiplied with the I2 weight matrix, then you'll get the value of 1.6. So the weight matrix, the input weight matrix is the same. That is a bias element 11011, and the weight matrix for the number 2 is 0.346290. That is 60 if you multiply. Obviously, NC times anything is going to be 0. NC, that is 0, that is 0. And then these are multiplied, that's 0.34, that's 0.62, that's 0.9. So if we add all of them together, you get is 1.86. Again, to get the I2 values, you go look for the row corresponding the element number 2. That there's the weight matrices, and multiplied with the input vector, you'll get IL2. And then obviously use the linear transfer function to compute the values of y out. So this way we can we know how to compute the input activations from I1 to I5, and corresponding values of y1 to y in of 1 to y in of 5 value. Once you have these activations, now actually I can apply this input activation to the output layer to get the values of yn. To get the value, for example, say here element number 1 yn, we have to take the output layer element. See, this is the weight matrix. you multiply this weight matrix with the input activation. Input activation that you have is this vector. If you multiply this vector with corresponding I1, which is this row, that is 0.763498 and so forth. You multiply that with the input vector here, which is going to be 1.84, 0.1.86, and the last one is 0.1.12. So if you multiply the corresponding elements and one times -76, 176, and so forth, if you multiply and add them up, you'll get 842. Obviously all these things are rounded to the second decimal place, then you get the sum. And here the to get here the values of y, output weight matrix uses what is called the Perceptron transfer function. What it means is for I greater than 0, y is going to be I. If I is less than 0, y is going to be 0. That means is it's a unipolar continuous. It's also called positive linear transfer function. Now you would see that in this case is less than 0, therefore it is going to be less than 0, y is going to be 0, y is less than 0, that is going to be y equal to 0, y greater than 0, that means I that is 0.3, here is 0.62 is greater than 0, therefore y equal to I, that is 0.62. Now what we have is once you compute this value of y, now we know here what our desired value was. We need to get 1001, whereas what we got is 0011, and also the none of them are matching, and therefore this network need to be trained. That means with the threshold of 0.22, this has to be we have to get 1001. That means this element has to be trained such that its minimum value it has to be greater than 0.8. This value is at 0 and 0, that means this value has to be less than 0.2 or less. This has to be 0.2 or less, and this value has to be 1, that means this value has to be greater than 0.8. So train such that this is greater than 0.8, that is greater than 0.8, and these two elements are going to be less than 0.2. And that's what actually is going to be done during this training. And let's look into this, how this training is done. Again, Perceptron neural network training starts here. Again, these are been reprinted, that is the fixed activation. Remember, this is the input weight matrix is a fixed weight matrix, and the inputs are fixed, and therefore each time you go through a training cycle, this is not changed and that's not changed, and therefore the corresponding activations are not going to change, and therefore they are computed only one time and they are fixed, and those values are the same thing as that are computed here. See 1.8, 4.86, 0.12, and those values are the same as what we have here. Those are fixed values. Okay, now what you want to do is we have computed the sums and activations for the previous one. This is actually during single cycle. This is what we have here, that is 002362 to start with. Obviously this needs training because this is not 1, that's not 1, this is not 0, that's not actually this is 0, this is fine. This is not trained, it should be less than 0.2, but it's slightly more. So this is fine. Only thing that is trained in this case, only this is trained, this is not trained, it's not less than 0.2, this is not trained, it is not greater than 0.8, it is not trained because it's not greater than 0.8. 1 0 0 1. Oh, that is the desired values, that's right here. Okay, now what you want to do is to make these changes, you want to do the modifications to this weight, that's only the output weight matrix. This output matrix is 0, 1, 2, 3, 4, 5. Output matrix is going to be 0 to 4. These weight changes are given by del. In general, is weight change will be given by weight change is given by del is equal to alpha times yi times d minus y. Alpha is the training coefficient, and then y is the input, and d is j. In this case, the weight change del of ij, that is from, this is your I, this is from j. So this weight, how much is this weight of w of 1 to 4? W of 1 to 4 will be given by, in general, delta ij. I is source again, and j is the destination. Now in this case, w of ij in this case in general is given by tc times yi times dj minus yj. In this particular case, I is 1 and j is 4. Therefore, there is going to be del of I4 tc. In this case, source is going to be 1, that is y1, yn of 1, times the destination dj in this case is 4, that is d4 minus y4 computed value. So that is going to be training coefficient is fixed in this case is 0.5. Yn1, you see this yn1, it is computed yn of 1 is the, what we have is now if you look at this weight matrix changes here, del of I4 is equal to training coefficient 0.5 times yn is yn1. You see the yn1, this is the activation 0.84, element number 1, and then that is the 1 to 4, and then destination, what is the desired value? The desired value here in this case d4 is 1, and that is the that's 1, and then the minus yj, that is y4. The computed value of y4 happens to be the value of computed value y4 happens to be here the 0.62, that is the activation. The desired value is 1 and the computed value is 0.62, so that's going to be again d4 is 0.62 and the desired value is 1 and computed value is 0.62, and input activation yn is 0.84 times 10 coefficient. So what you are going to get is actual value is going to be 159, when it's rounded it is going to be 0.16, and that's the amount of change that you're going to make for the output weight matrix. For that element you change by minus 0.16. Similarly, if you look for weight change that you want to make, say for example for this element which is from 3 to 1, so del of ij, that is I is 3 and j is 1, 3 to 1 equal to yn of 3 times delta 1 d1 minus y1. Now in this case 10 again that's fixed, and the yn of 3, what is the value of yn of 3? Here you got yn of 3 in this case here is 0. Yn of 3 0.46, and the desired value is for element number 3 is again the del of 3 1, again the training coefficient is 0.5, yn of 3 happens to be yn of 3 is minus 0.46. The value of the desired value for element number 3 happens to be desired value for the element number 1 is 1, and the computed value happens to be 0, and therefore the value of the 10 coefficient is going to be 0.5 times minus 0.6 times 1 minus 0, that's going to be 0.23, and that's what the value that we have here. Okay, once you have that and the training coefficient, this is the amount of weight change that you make to the original weight matrix. To get the new weight matrix, what you do is you take your world weight matrix and add the corresponding weight changes, and then you can get the new weight matrix. Here this is a new matrix. So here again this weight matrix is nothing but W dash equal to old weight corresponding elements, add the corresponding weight elements in the delta to get a new weight matrix. So what it means, if you look at the what is the weight matrix, old weight matrix. Old weight matrix was for example, if we take this 5 to 5, here the old matrix is 0.42, and then add the weight change happens to be 0.22, and then add them together, new weight matrix is 0.20. Similarly, if you want to look for say this element from 0 to 3, the original element was 0.14, when you add 19, then you'll get 0.33, that's a new element. Okay, once you have that, the new weight matrix, then actually again the input weight matrix remains same, output matrix is going to be different. So when you go through the fixed activations, again they are reprinted, which is the same as the original one. When you apply the same weight matrix to this new weight matrix, now you get the new weight matrix is the corresponding activations comes out to be these are ILs, and the INs are 2.79. The second one is 1.49. So if you apply transfer functions, I greater than 0 is going to be I, that the I less than 0 is going to be 0, that is going to be 0, that is going to be 2.1. Now this network is trained because the for one this element has to be greater than 0.8, that's okay. For this it has to be less than 0.2, that's okay. This for 0, that is less than 0.2, that's okay. And for this one it is greater than 0.8, that is 2, and therefore that is also okay. That is now it is being trained. Now once that is done, the next thing that we would like to have is the you want to go into the recall mode, and that's what we're going to look in next in recall mode. Now the network in the recall mode, we store this network weight into. Again, once the network is trained, what it's going to do, it will say the network training is complete. And once the network is trained, these weight matrices like this weight matrix, which is final weight matrix, and also of course the original weight matrix, that weight matrix, both are going to be stored into a network file called the Perceptron CKT. So if you look at the Perceptron CKT, of course when you go into recall mode, it reads input data from this file and then uses that for recall. So if you look at this Perceptron CKT file, once it is trained, that the trained network weights are going to be stored into a file. That file is a Perceptron CKT ext file. So if you look at this here, this is a Perceptron CKT file. Basically what it does is it stores the n, which is the number of elements in the input, primary inputs on the input layer. It specifies the how many elements that you have in the output layer. Then it specifies the WIL, what is the input weight matrix, and then followed by WOL, which is the output weight matrix. Obviously input weight matrix has got it is a 7 by 5, that is 0, 1, 2, 3, 4, 5, and then output elements are 5 elements, 0, 1, 2, 3, 4, 5 here, where the output weight matrix is the 0 to 7 by 4, 0, 1, 2, 3, 4, 5, and by 1, 2, 3, 4, that weight matrix. So this, as you could see, this weight matrix which is same thing as this one, 0.26, 0.08, that is 0.20, that's what is stored here. When you go into recall mode, it is going to read this file and then does the recall mode, and that's let's see that in the next section. Again, as you could see, the weight matrix that is done here, it's read this input data file and redisplayed it, all the information, same the number of elements 4, number of output element 4, and they redisplayed this input weight matrix, that is 0, 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5, and that's corresponding to 1, 8, 2, 99, which is NC means actually when it stores all the NC connections are stored as 99. So when it reads it back, wherever it appears 99, it puts like NC here, back here. Output elements of course is fully connected, and therefore there are no NC connections here. 0.26 and then 0.20. Again the inputs are 0, 1, 2, 3, 4, 0, 2, 5, and then on destination. So these are essentially, this information is the same as what you have here. Once that is done, then what we are going to do is you apply a test input in this case, and correspondingly you'll be able to, it will go through, essentially does a forward pass for a given input values of x input. We enter text input 1 to 5. This is a DOS command. So when you run it in a DOS command, it automatically stores the file into it. So when you apply this input 11011, that's what we are trained for. We have to get the output obviously as is. So and then what it does, for a given input, it goes and computes the value of the input weight matrix, input activations of the input layer, activations of the input layer, internal activations of the input layer, activations of the input layer. Then use this activation to compute the internal activations of the output layer and the corresponding output activation. So if you go and look at this, let's see how you got this one. This is when you multiply this weight matrix to get the value. This is the this is 1, 2, 3, 4, 5. That is this is I2. So to get I2, that we need to multiply the input activation, which is 11011. Of course, bias term you still have to have 1, and that's 1 multiplied with this weight matrix will give us 1.86. So the input is 111. That is the bias element 11011, and the weights are going to be 0.34, 0.62. This row. So if you multiply these two corresponding elements, you'll get I2 value in the input layer, that is 1.86. Again, it is since it is a linear transfer function, I equal to y, and therefore you will get the same values of the 0.84. This is a linear transfer function. Now once you have that one, then you use this internal activation to compute the internal summations of the output layer. So if we take this element here, this is number, this is I4. So I4 means this is the weight matrix, and you are going to apply these input activations multiplied by the corresponding elements of the weight matrix. You will get the value of the I4. So what are the activations? Activations are again the weighted elements. In this case are going to be first element is going to be 1. The next one is going to 0.84, 0.86. Those are the internal activations, and the corresponding weights are going to be 0.33, 0.42, 0.20. So you'll get I4. To get I4, you take this multiplied with the input vector, multiplied with this W vector, you'll get I4. So you'd add all of them together one by one, corresponding elements. You would get there is some error in here. We had to get actually 2.02, maybe actually, because when I rounded all these numbers to second decimal place, it possibly actually that added cumulatively added this number and came out to be 0.91, but that has to be 2.02 internally. That's because of running error, I think. So that you can get these output values. So now for any other inputs, if you apply different inputs, the outputs are going to be a different value. It's not necessarily you'll get the same value, but it is going to be different. So that in the test mode, for any given input, It reads the trained network weight, network matrices, and essentially performs the one forward pass. Apply the input, compute IL, compute YIL, compute IYL, compute YYL, and that actually gives you recall mode. What we have done, this is for one pattern, but when you do the training, recall is going to be the same thing. We are applying one and computing the output. That's not going to change. And if you have multiple patterns, what you're going to change is going to change only during the training. During the training, instead of having one patterns, you can have multiple patterns. So the once that is training is done, we still have the same one weight matrix for the input layer and one weight matrix output layer, and then correspondingly you can compute the corresponding output here. So that's Perceptron again is a very simple network for simple problems, but for complex problems we need to use backpropagation, which we'll be studying later on. That is all we had to say for now on the Perceptron neural networks. Bye.